In this video, we're going to look at a couple of different types of chemical reactions that occur in aqueous solutions. Now, reactions in aqueous solutions are among the most important classes of chemical reactions known. They're responsible for the chemistry of life. All the metabolic processes, all the biochemical processes that take part in our body take part in aqueous solutions. Reactions in aqueous solutions are responsible for the chemistry of the environment, particularly the aquatic environment or wherever any water is present. And reactions in aqueous solutions are also amongst the most important industrial processes as well. When we're considering reactions in aqueous solutions as students of chemistry, we're likely to have to do at least three things. The first thing we're going to have to do is to be able to predict the products of a chemical reaction based on a given set of reactants. So in order to be able to do that, we first have to identify the type of reaction that is taking place. Three types of reactions that we'll consider. The first is precipitation reactions, where two aqueous solutions are mixed together and we get a formation of a solid ionic compound known as a precipitate. And sometimes those reactions can be spectacular, as in the formation of lead iodide shown in the picture there. Acid-base reactions, otherwise known as proton transfer reactions, are another important class of reactions that we will consider, and we need to be able to know how to identify acids and bases and therefore whether an acid-base reaction is likely to occur. Acid-base reactions rely on protons. They're known as proton transfer. In other words, the H plus ion or the hydrogen ion becomes important in acid-base reactions. The third class of reactions that become important to us are redox reactions, otherwise known as electron transfer reactions. And as I said, we'll deal with all three in some detail later on. If we know the reactants in a chemical reaction and we know the products, then we can write down an unbalanced chemical equation. And for example, what we've got here, two reactants. We've got solution of calcium nitrate here and a solution of sodium phosphate. This particular reaction happens to be a precipitation reaction, and we can write down the products over here: calcium phosphate and sodium nitrate. So when we write down the products of a chemical reaction, it's important to ensure that we get the correct chemical formula for each substance. So, for example, Ca3 brackets PO42, is this the correct chemical formula for calcium phosphate? And we're going to have to ask ourselves this question every time we write down the chemical formula for a product. For example, is calcium phosphate, does it form the salt CaPO4, where the calcium ion and the phosphate ion come together in a 1-to-1 ratio, or do they come together in a 3-to-2 ratio, as in this representation here, Ca3PO42? Well, calcium phosphate is made up of calcium 2 plus ions and PO4 3 minus ions, and we're likely to have to look at working out the chemical formulas using the crisscross method a lot of times, particularly when ions are involved. So we can take the 2 from the 2 plus charge of the calcium and bring it down as a subscript of the phosphate ion. We can take the 3 from the 3 minus charge of the phosphate and bring it down as a subscript for the calcium ion. And so what we end up with there is Ca3 brackets PO42. And we see that that is the correct chemical formula as we had written it for calcium phosphate. Chemical formula for sodium nitrate: sodium is a +1 ion and nitrate is a 1 minus ion, and they come together in a 1-to-1 ratio. Having written down the chemical formulas for the products correctly, we now balance the equation, and the only way we can balance the equation now is to put the big numbers out the front. We need to use stoichiometric coefficients to ensure that we get the same number of atoms on each side of the equation. As part of balancing the equation, we want to identify what subscripts will the products are most appropriately expressed as. So, for example, calcium phosphate, most phosphate salts are insoluble, and the only exceptions being the group 1 metal salts, sodium phosphate, lithium phosphate, potassium phosphate, etc., and also ammonium phosphate. So calcium is not one of those exceptions, so calcium phosphate will form an insoluble salt and will therefore have the S subscript. Sodium nitrate will have the aqueous subscript. There's two reasons for that. All sodium salts are soluble and therefore have the aqueous subscript, and all nitrate salts are soluble. So we've got two reasons to put the aqueous subscript next to the sodium nitrate there. Most chemical reactions in aqueous solutions are some type of displacement reaction. And a displacement reaction involves an exchange or a displacement of parts between reactions. So for example, if we consider the general reaction scheme here, A plus BC going to AC plus B, we can see that the element A is going to replace element B in this compound to form the compound AC, and then elemental B gets formed as one of the other products. This is known as a single displacement reaction, as there's only an exchange or a displacement between one part of the reactants. We can also have double displacement reactions, and these are also known as metathesis reactions. So in the general reaction scheme here, A plus B going to C plus, or plus CD going to AD plus CB. What we can see here is that A would replace C to produce the compound AD, and at the same time B would replace D to form the compound CB. So a couple of examples of single displacement reactions. We've got metallic zinc reacting with sulfuric acid. This is an acid plus reactive metal reaction, and it forms the zinc sulfate plus elemental hydrogen gas. Bubbles are being evolved, and you can see that in the photo. What happens here is the zinc effectively displaces the two hydrogen atoms to form the zinc sulfate, and then elemental hydrogen is released. So that's an example of a single displacement. Another example here, we've got zinc metal again, this time in a copper sulfate solution, and it's producing the zinc sulfate salt plus elemental or metallic copper. What happens here is zinc is effectively displacing copper from the copper sulfate salt solution, and we form zinc sulfate, which is aqueous. Sulfate salts are generally soluble, there's only a few exceptions, and the other product that's formed here is metallic copper, which forms on the surface of the zinc, as you can see in that photo there. Now these two reactions are example of redox reactions or electron transfer reactions, and as I said, we're going to go into those in a lot more detail later on. An example of a double displacement reaction, these are the classic precipitation reactions. These are all the double displacement reactions, are also known as metathesis reaction, and there's an exchange of two parts here. In effect, what we're doing is swapping anion and cation pairs. So in this particular example here, we've got a solution of silver nitrate and a solution of sodium chloride. Now all nitrate salts are soluble, so silver nitrate being an aqueous solution, all sodium salts are soluble, so we have two aqueous solutions there. However, when we mix those two solutions together, we actually form silver chloride, and silver in the presence of chloride forms an insoluble precipitate, and so we got that solid subscript there for the silver chloride. The other compound that's formed is sodium nitrate, and again we see that we've got two reasons for that to be an aqueous solution. It's a group 1 metal salt, sodium salt, and all group 1 metal salts form aqueous solutions. It's also a nitrate salt, and all of those are soluble as well. In effect, what's happening here is the silver cation is displacing the sodium cation, and we get the silver chloride formed, and the nitrate anion is displacing the chloride anion, and we get the sodium nitrate formed. So this double displacement or metathesis reaction involves an exchange or a swapping of anion and cation pairs, and we get the solid insoluble sodium chloride formed there. And precipitation reactions being a classic example of double displacement or metathesis reactions.